Hi, Kevlin.
Hi, Andrei.
Hi.
How is it going?
Hi.
So, before we start, I have a small question to you. Kevlin,
Yes.
what do you think? What is the biggest pain for test engineers now?
Software. Other people. well, let's be honest. There is a deep truth to that, isn't there? It is both. As with many things in life, it is a source of joy and a source of pain. You do not apparently get one without the other. But yes, it will be software.
Okay, and what is the biggest solvable pain of engineers?
Funnily enough, software. Because ultimately, if you look at it, software is the thing that we create. It is ours to control. There are a load of things that we cannot control in life, and we're not very good at people. People are complex. People are very difficult. But software is the one thing. We create it. We also create our own problems within it, and we are also able to solve them. So I think software is both the problem and the solution.
Yeah, and more problems we create, more work we have, so, right?
Exactly, yes. I think it keeps everybody in a job, although that's a very cynical way of looking at it. But yes, there is a certain truth. We are always, with every solution that we come up with, we have two problems. One is, how does everybody know about the solution? I think we often deal with that. Many people, when we talk about things like testing, and my particular area is unit testing, this is not a new idea. So why doesn't everybody do it or do it well? Because there are so many things to know. We cannot know everything. And so that the first thing is, even if we do have a solution, our challenge is, how do other people know about it? How can they apply these skills, whether it's a soft skill or a hard skill? How do they know how to apply it? So yes, every new thing creates at least two more problems.
Yeah, I'm absolutely agree with you.
So, is it truth that your talk will give us part of the answer about how to fix some issues with software?
Yes, I think what I'm going to try and offer you is kind of the other side of what do we mean when we test. In fact, I did a talk for Heisenbug last year, what we talk about when we talk about unit testing. And this is kind of like a sequel, and it's very much looking into the structure, because the biggest problem that people have once they have tests is, are they any good? Are the tests understandable by people? Or do the tests become part of the technical debt of the project? So there is this idea that our tests can communicate more than just it passes or it fails. We can actually communicate something about the structure and meaning of the software. So in that sense, that is what I'm going to offer you. The hard part is making sure that other people now understand that that is what is being offered, and that they can do something with that they can do it for themselves.
That's really, really great. So I think we are ready to start the talk. Are you ready, Kevlin?
Yes, I am indeed. Yes, let's go for that.
Let's start. Yeah.
Right. Okay. As if by magic. Right. Just so that people know, what I'm going to be doing is we'll be taking questions. You can put questions in the stream, but I'll handle the questions at the end. It's a little bit easier than trying to interrupt the stream. It's not quite like being in a room. I think that would be great, but perhaps we'll do that another year. So here's the door. What am I going to talk about? Structure and interpretation of test cases. Now, that's kind of an interesting title. It has a very particular reason for being. The title is taken from this book. It's kind of a computer science classic, Structure and Interpretation of Computer Programs by Abelson and Sussman. And there's this lovely observation in there. Programs must be written for people to read and only incidentally for machines to execute. Now, I think that is a kind of an important observation, because we might say, well, surely the whole point of code is that it should run as software, that software is useful for somebody. Yeah, I think let's understand there are three basic audiences for code. And two of the audiences care about the code, and one of them cares mostly about the consequence of the code. The audiences that care about the code, that is the software developer and the compiler. The audience that doesn't care so much about the code but cares about the consequence is the customer. It's the consumer, whoever it is that is going to use the software, whoever it is that wants functionality from the software. They care about the consequence but not the detail of the code. But when we come to the two audiences that care, it turns out that one of them is actually quite easy to please and easy to satisfy, and that is the compiler. So there are days, certainly, when we wrestle with the compiler and sometimes feel like we lose. But that is actually the easiest audience to communicate with. It requires a formal notation. A programming language is a formal notation. It requires an understanding of the syntax of the language, and the syntax of any programming language is always going to be far, far simpler than the kind of the messy syntax of natural languages and human communication. It turns out that our biggest challenge is an audience that cares very much about the code. And they care about bridging all of these audiences. They care about the compiler and they care about the consumer, the customer. And that is the human who is the software developer. So this is our target audience. And when we say programs must be written for people to read and only incidentally for machines to execute, this also applies to our test code. And I think this is an important consideration. We often, when we approach testing, and my focus today is on unit testing, we don't really focus on the meaning. That's why I've talked about this as being the structure and interpretation. Rather than just ending up with hundreds and hundreds of unit test cases, each of which might individually be useful, but when we look at them together, we don't really fully understand what's going on. We might say 500 tests were executed, 500 tests pass, or 499 tests pass. What is the meaning of the one that fails? But what is the meaning of the other 499? Unfortunately, we have got ourselves to a point where we tend to think of tests as sometimes a second-class citizen of our software system. And when we talk about testing, to many developers, they think, right, yes, unit testing frameworks. I have a lot of those on offer. Yes, okay, I'm working in Python, so I guess I could use unit test. But if you're a Python programmer, honestly, I'm going to recommend using PyTest. If I'm in C#, I'm going to be thinking NUnit. If I'm in Java, I'm going to be thinking JUnit. And so on. Each one of these has the answer. Every programming language has at least one or two answers for the testing framework. But that's not really the challenge of testing. It turns out that we are not understanding ourselves. So there's this really nice piece by Todd Golding. It's a few years back. It was in Better Software magazine. And he captures what I think is a very common experience for developers. The programmer in me made unit testing more about applying and exercising frameworks. I had essentially reduced my concept of unit testing to the basic mechanics of exercising unit testing frameworks to verify the behavior of my classes, this very narrow view. My mindset had me thinking far too narrowly about what it meant to write good unit tests. Now, notice here, we're not saying that we are not attempting to verify our behavior or give ourselves confirmation. We can never test everything, but to give ourselves confirmation, to give ourselves confidence of the behavior of our code. But it needs to go beyond just the personal point of view. It needs to be an act of communication. A good unit test, in fact, let's focus on that, good unit tests. It's not just enough to have unit tests. We want to have good unit tests. Or as I often talk about it, guts. How do we program with guts? So in this, we need to understand, what do we mean by unit test? It's a term that has been around for, I don't know, since the 1960s. But it does not have one fixed meaning. It has a number of possible meanings. So which meaning is the most useful to us? And then what do we mean by good? Because that is the value judgment that will make the difference, to judge its value. The idea of a test as an act of communication and not simply an act of verification is what is going to give it extra life within our project. So I'm going to offer you a definition that is fairly close to definitions that many people use nowadays. The idea, for some people, unit test just means a programmer level test. For other people, unit test means, I'm testing a class, but that can't be our definition of unit test because there are lots of languages that do not have classes. There's also the other problem of, do we mean a class without using other classes? I've seen that definition before. It's not very useful because, of course, the whole point of classes is that they are built using other classes. So here's a definition that gives us feedback about the quality of our system. So what I want to try and communicate today is this idea that our tests and our structure are woven into the meaning of our system. So the definition, as I wrote, a definition that I find useful that I wrote a few years ago, a unit test is a test of behavior whose success or failure is wholly determined by the correctness of the test and the correctness of the unit under test. In other words, if the test passes, it's because of our code and because of our test code, our production code and our test code together. If our test fails, it's because of our production code and our test code. In other words, there is nothing else. There is no third element of any kind. In other words, we are isolated from external dependencies. What we define to be a unit is something that is isolatable from external dependencies. We do not control external dependencies. We do not control things like the network or the file system. We do not control time. All of these things would be interesting. We can influence them, but we do not control them. So let's first of all consider kind of the picture that we're getting from our code. And I divided up our code into 3 parts. There's the part that is unit testable, that satisfies that definition. There is the part that is necessarily not unit testable. Okay. And what do I mean by that? I mean that there is some part of your system whose job is to touch and deal with the external dependencies. Otherwise, your system is probably quite boring. There is a bit that must talk to the database. There is a bit that must use environment variables, registry variables, must access system date and time. These are all accessing things that are external and beyond our immediate control and our guaranteed control. And of course, our code is going to use them. And there's nothing wrong with the fact that they are not unit testable. We acknowledge that. That's fine. We can test them. We can wrap them. We can put interfaces around them. This is all good. The problem category, though, is the third one. It should be unit testable, but it isn't. That becomes the issue. There's a little gap here where you describe it to somebody. They go, oh, yeah, you can unit test that. And you go, oh, well, no, actually, I ended up using a file in this case or something like that. And that is the problem. That's where we're getting feedback. Our tests are our first interpretation of such tests is that they are telling us that we can improve our system. It's like feedback. This is a code review for us. Now, I used this diagram when I gave a talk at Heisenbug last summer. And I'm going to go a step further. I want to show you what a good code base looks like. A good code base looks like this. It's got a minimal amount of code that is not unit testable. Okay, there's always going to be a little bit. We are not perfect, and there's always some amount that we're always thinking about and reasoning about. And then a code base that is, well, what we might call legacy or problematic or high and unmanaged technical debt. Things depend on external dependencies that cause us an inability to be able to test them directly in the way that we would like in a unit sense. So from my point of view, we have a decent definition of unit test. A unit test is a test on any code that is isolatable from external dependencies and is therefore completely under our control. And therefore, when it passes, we know that it is because of our code. When it fails, we know that it's because of our code. It's as simple as that. There's no case that the network is down, the passwords have changed, or we don't have the permissions. We need to now look at this question of good. So I published this book last year, edited it with Trisha G, 97 Things Every Java Programmer Should Know. And there's this lovely definition or a series of discussions from Mariet van Dijk in her piece, Using Testing to Develop Better Software Faster. She talks about this idea of a failing test should tell you exactly what is wrong quickly. Now notice what she's focusing on here. She's focusing on communication. The idea of the test is that it communicates. The body of the test communicates. The name of the test communicates. Its failure communicates. In other words, we want our tests to be useful when they fail. That's the point at which they can tell us the most. Without having to spend a lot of time analyzing the failure. This means each test should test one thing, make your tests cohesive. We have the idea of cohesion for production code. The same also applies to tests. They should have one thing that they do well, one focus. We should use meaningful descriptive names. Now, the thing is, everybody tends to think they're using meaningful descriptive names. We'll have a look in a moment at what we mean by that. But Marie clarifies it, saying, well, don't just describe what the test does either. We can read the code. Tell us why. We need to communicate something about the problem domain. We need to communicate something about the purpose of the code, the why of the code, if you like. So this can help us decide whether a test should be updated in line with changed functionality or whether an actual failure that should be fixed has been found. And this is an important idea. When things fail, they fail either because something is genuinely deeply wrong, we would call it a bug, or because we have updated something somewhere else and we have not updated this test to reflect the current functionality or understanding of it. So in one sense, it is a bug because we forgot to change it, but it is work in progress as opposed to a discovered fault. And then there's a very simple observation that Marie observed: never trust a test you haven't seen fail. Now, what's interesting about this point is that it is quite easy to write tests that accidentally always pass, that they miss testing the thing that we care about. And there are two cases that can help us, or two techniques that can help us understand whether or not our tests can fail or not. I think one of the simplest is test-driven development, because there you're encouraged to write tests that first fail, because then you are understanding that you are dealing with a behavior that you have not yet implemented. But also, if we occasionally modify the code just to see whether it does fail when it's supposed to, and this is and we can do this either manually or we can actually do this automatically using mutation testing tools. The idea there is to understand, increase confidence. Yes, our tests are doing something useful. They are not just doing something superficial. We're not going assert true or anything like that. So what is another quality of good tests? Coverage is a concept that people normally talk about. And Brian Marek observes, I expect a high level of coverage. Sometimes managers require one. There's a subtle difference. We want to avoid the case where we make coverage a goal, a project goal. We must reach a particular number. And there are a number of reasons for this, but one of them is, first of all, we have a very simple idea of coverage. When most people say coverage, what they actually mean is statement coverage. And this is important. We've got such a habit. If I look at most coverage tools, I was looking at something in Python yesterday, and again, coverage tool was reporting coverage. It just said coverage. It didn't say statement coverage. It just used the word coverage. I try to discourage people from just using the word coverage, except when they mean it collectively. There are many forms of coverage. Statement coverage is the easiest to measure. It is also the easiest to describe. It is what percentage of statements have we touched in the code when we executed our tests. It doesn't say anything about whether or not our tests are meaningful, but it does give us some kind of confidence. Have we actually executed code? Now, in some cases, we would say, well, we want to get close to 100%, and as close to that as possible. That's great, and there is value in being that high. For a start, you can easily spot code that is unreachable the minute you drop below a high value. But there is a problem with always focusing on 100%, is it makes us think that we are done. If we get to 100 or close to 100, we think that we are done. Why? Because 100%, that means done. This is what you were taught at school. When you are 100% complete, then you are complete. So the problem is that it's not done at all. Statement coverage is only one form of many kinds of coverage. There's function coverage, branch coverage, loop coverage, condition coverage, and multiple condition coverage. Multiple condition coverage is a stronger form of condition coverage. Loop coverage is a stronger form of branch coverage. Function coverage is probably the weakest of those I've listed here, which is why I haven't worried about it on the screen. There are other forms of coverage that go further and further down. These explore how many paths through the code that you take. It is quite possible to have 100% statement coverage, but have below 50% branch coverage and even lower loop coverage. So there is this idea of trying to achieve and understand the kinds of coverage by always reminding people that you're talking about statement coverage. You don't fool yourself into thinking that 100% means done. You have not explored all the combinations in your code. So that's a reminder. It is quite easy to forget whole categories of kinds of things. So I tend to think that it's a useful statistic, but be very careful about pushing too hard on it. Numbers fight back if you push on them too hard. What I want to do is focus on the kinds of coverage. What are the cases? In other words, let's explore this from the domain's point of view. So common cases. What are the cases that where we're going to be using the code that are ordinary and typical and common, the usual cases, if you like? The ones that are representative of the kinds of data that we might expect to be using with our functions and our classes. And don't forget the simple cases. I often find people will overlook the simple cases. Why? Because they go, oh, well, I don't need to worry about the simple cases because it's the common cases, it's the typical cases that matter. The simple cases, they're too simple to test. We won't get those wrong. There's no point in testing those. I remember once having a discussion with somebody who spent 20 minutes justifying to me why he wouldn't write a test that would take him 5 minutes to write. The point there is, if it takes you longer to explain why you're not going to write it, then just write it. But there's another point here. We have a blind spot. Just as we have a blind spot in our eye, we have many blind spots in our testing. We overlook the simple things because we can't imagine how we would get them wrong. And yet, when I use software on an everyday basis on my phone, on my laptop, or when I'm walking the streets and I just see signs, how many of them are simple cases that have just been overlooked? Typically overlooked because we are so busy focused on the complex cases and the typical cases, we overlook the simple ones. Now, the diagram shows some simple cases are also common and some common cases are also simple. We also have boundary cases. Some boundary cases are simple. Some of them are actually quite common. So let me describe a boundary case. My coffee cup that you can see here is almost empty. Emptiness is a boundary case. It is also, sadly, a very common case. It is also a simple case. You can see that there is an overlap of these three categories on this diagram. It's a Venn diagram. But this Venn diagram also allows you to overlap four, the way that I've done it. It's kind of like a tulip of testing. Error cases, we have a real blind spot about those. Some errors are very common, some are very simple, some are very good examples of boundary cases. So this Venn diagram you see on the screen, this kind of like flower, this tulip, shows you all of the ideas that these are not mutually exclusive cases. But what you should be doing is when you're looking at a test suite, when somebody shows you a set of tests or when you yourself are writing them, go through and make sure, have I remembered the simple cases? Do I just have the common cases? Or have I been so focused on the boundary cases because I don't want to miss them? The edge cases are where people often are aware that they're going to make a mess and trip up. So sometimes people are so sensitive to that they spend all their time focusing on the edges, but they forget the common behavior that is not at the edges, and so on. Just make sure you have representatives of these four categories. So I'm going to pick an example that I used last year, the idea of the leap year, but I'm going to do a different language. I think last year I did this one using C# and NUnit. I'm going to use C++, but I'm going to use basically C, and I'm going to use Google Test just for a change. And it's determining whether or not a year has a leap year, a 29th of February. Simply a function that takes a year and returns a true or false status. Now, the simplest way people might want to test this is by saying, I have a test function, and they go ahead, test, and they call it test, and they call it is leap year. Well, we're overusing the word test here. I think we can already see this is a test. But then people kind of look around. Google Test has a two-part name system. So what are the two parts of our names? Well, sometimes people will go ahead and say, oh, test is leap year is okay. Well, yes, I hope so. I mean, why else would you be testing it? I've seen things like is okay, is correct, test is leap year works. The one I saw at a code review a few weeks back was test is leap year works as expected. Now, the point here is that tells the reader absolutely nothing about what you're expecting. That knowledge is not transferred to me. I don't know what works as expected means. If it's green, then I understand it works as expected, but that has not communicated knowledge to me. I don't know how to interpret this. The tests need to explain what is expected. The tests need to be a specification, a description. We'll also see that we've put all of our tests in one function here, so perhaps we should split this up. Now, the minute we split things up, people immediately are tempted to number them. So test is leap year 1, test is leap year 2. No, this is a terrible naming scheme. It doesn't tell us anything. So let's start looking to the domain. The idea is our job here is an act of communication. The first thing we might recognize is that there are leap years and non-leap years. We might decide under leap years, let us pick 2020 last year and the year 2000. These are both leap years. However, if we understand what makes a year a leap year under the Gregorian calendar, we may recognize that 2020 and 2000 are not leap years for the same reason. But that's not visible on the screen. That's not visible as the rule. You have not yet explained to the reader the different cases. Now, one area and one way that people like to do this is they like to then embed the test data in the name. I'm going to discourage you from doing this. First of all, this doesn't help at the moment. Test is leap year 2020, test is leap year 2000, test is leap year 2021, test is leap year 1900. At this point, you don't yet know which is a leap year and which is not. So let's improve this. There we go. We discover that 2 of them are not leap years. 2020 is a leap year, 2000 is a leap year. This year is not, and 1900 was not either. So first of all, be explicit. The whole idea is communicate to the reader. Don't say, well, you know. Don't assume that they do. One of the reasons I use leap year as a simple example is because, 1, it is simple, and 2, most people get it wrong. It is something that is so simple and everyday that we don't fully understand it. So here is a perfect opportunity of understanding how we can explain to somebody what we mean. But there's another reason, although we've been more explicit here, there is another reason to not focus on the magic numbers. Because 2020 is not significant in the domain of years. 2021 is not significant in the domain of years, because I could easily change every one of these to another example, and that means that I've now just changed, the data. But notice I haven't told anybody when is a year a leap year. Notice the one thing we have not said. We've given them examples, but we've not given them a rule. We've not given them a model of understanding. We have not communicated the fundamental model of the domain. This is a better approach. A year divisible by 4 is a leap year. A year divisible by 400 is a leap year. Well, this is not going to fit on the screen, so let's rearrange it. This seems a little bit better. Let's reorder it according to the size of the data set or the size of the equivalence class. The largest class of years is years not divisible by 4. Okay. A year not divisible by 4 is not a leap year. A year divisible by 4 is a leap year. A year divisible by 100 is not a leap year. At this point, we discover there is a contradiction. All years divisible by 100 are also divisible by 4. At this point, we discover what it is that we mean. What we mean to write is this. A year divisible by 4 but not by 100 is a leap year. So notice one of the things we're doing as we write our test is we are reordering and we are clarifying and communicating to ourselves. And if we're pairing or mobbing, we are communicating to others. Or importantly, we're coming back to the test code later. Do not assume that you know everything that you need to know when you first start writing a piece of code. If you are writing your code and your tests together, you are learning how to talk about your code. And our names will get better with time as we have better understanding. So it's a process of clarification, or if you like, a process of iteration. So we have an idea here of communication, and we've also got a sequencing. In this particular case, a year not divisible by 4, that's kind of like a precondition, or it's a given, and then is not a leap year, and that's an outcome or a postcondition. I'm going to reverse these here for a very simple reason that becomes a little more apparent later. I'm going to go with the conclusion. A year is not a leap year if it is not divisible by 4. A year is a leap year if it is divisible by 4 but not by 100. Now, this gives me a very pleasant structuring. It gives me the outcome first and the condition second. That's not always the right thing to do. But in this particular case, I'm taking advantage of something in Google Test. In Google Test, it will group together when the presentation of test cases which have the first part the same. So in this particular case, a year is not a leap year will group with a year is not a leap year. These two tests, the first and the third, will group together in presentation. So yeah, I will be influenced by my choice of testing framework as to how it presents things. You also notice that the names are very clear. They are basically, once I remove the underscores, we have a very clear communication of the intent. So what we're doing here is I'm going to pick up on a piece program with guts that I wrote for 97 Things That Every Java Programmer Should Know. What we're trying to get across here is what's the purpose of your test? To test that it works? That's only half the story. The biggest challenge in code is not to determine whether it works, but to determine what it works means. That's our biggest challenge. When somebody says it works, it's like, yes, and show me what I'm expecting. What am I expecting from leap year? And importantly, if we look at it from this point of view, if I give you an implementation that's the basic Gregorian leap year rule, then all of this passes. If I give you the Julian calendar rule, then we will see that 3 out of 4 of them pass, but the one that does not pass, we now understand what is not working. Notice the name. A year is not a leap year if it is divisible by 100, but not by 400. Well, apparently a year is a leap year if it is divisible by 100, but not by 400. In other words, the contradiction of the name has been negated. It has failed. So everything looks okay at this point. We go back to our tulip. We actually realize the one we haven't got is error cases. Well, I'm going to create a calendar here, an arbitrary calendar. I'm going to say, let us support a proleptic calendar. Proleptic means backdated. The Gregorian calendar has not been supported forever. It was introduced in the late 16th century and kept on being rolled out until the 1920s. I think officially Turkey was the last country to adopt it in the 1920s. So what we're going to do is, just to keep things simple, I'm going to say we have a common era calendar that is Gregorian. Therefore, everything from year 1 onwards is okay, and everything before that is not okay. So therefore, I'm going to make year 0 an error case. I'm going to assert that is leap year of 0 will throw, and it will throw a standard invalid argument exception. I will demonstrate that. I will also say a year is not supported if it is negative, for which we write a very similar outcome. But again, another thing we want to see from our tests is when we look across them is a clear body of meaning. The idea that, well, if it's not, it's not supported. When is it supported? You will see all the examples that we would likely have used have been positive, but confirm for the reader. Make sure that the reader is satisfied with what you've said. A year is supported if it is positive. Now, strictly speaking, if I'm doing C++, I will use the standard numeric limits trait, but actually, let's just keep life simple. More people will understand this. Int max, the maximum value of the integer. In other words, I'm basically saying that the full positive domain, we've seen the low numbers of years and years like 2020 and 2021 being used as example data. What I'm going to do is say the whole of the positive domain. There's no magic cutoff at the year 10,000. And again, we have these very clear, meaningful pieces of communication. Okay, so that's a nice simple function. Let's take this further. What we have here is a stack of rocks. In fact, it's the Seven Mountains kind of rock sculpture outside Las Vegas in Nevada. Let's talk about stacks, possibly the most over-specified and over-implemented abstract data type in computer science. What is the vocabulary of a stack? What are the words we associate? Well, a stack, we can create one. It's new. We can push. We can pop. We can find its depth. And we can find its top element. So that's the language of the stacks. What is an abstract data type? Abstract data type is often actually what we implement when we use classes, particularly classes without inheritance and in statically typed languages. Many people are not aware there's a subtle distinction between object orientation and ADTs. If you're working in Java, you're working in C# or C++, probably most of your classes are actually ADTs rather than object-oriented classes, but that is a discussion for another day. The idea of an abstract data type goes back to Barbara Liskov and her work in the 1970s. And if you're familiar with Liskov's substitution principle, yes, it's the same Barbara Liskov. An abstract data type defines a class of abstract objects which is completely characterized by the operations available on those objects. Now, we could formalize it with a nice little piece of mathematics here. We made it generic for all T, for all types. It's generic. There is such a thing as a stack. There exists a stack such that there are the following 5 named elements, new, pop, push, depth, and top, which have the following signatures. New gives us a stack of T. Push takes a stack of T and a T, whatever our type is, and it gives us a stack of T, the resulting stack after a push. Pop takes a stack and it gives us a stack that is reduced. It doesn't always do this, hence there's a line across it. An empty stack, we're going to say that's an error case or not specified by a model. A depth takes the stack, returns an integer, and top will take the stack and give us a T, whatever that type is. Now, this is unfamiliar notation. Let's turn this into Java. So I've got a stack of T, I've got a constructor, I've got a push, a pop, a depth, and a top. I'm going to make pop a pure pop or a strict pop rather than the common convention, which is to return T. I'm going to keep things a little bit simpler. And we have a very simple idea. There is some very simple operations that we could do here. The question then is, what do my tests look like? And this is a really kind of common approach. People end up going test constructor, test push, test pop, test depth, test top. It's like, well, we already know it's a test. You don't need the word test in your test name unless you are relying on a testing framework that uses the name, reflection on the name. Typically, in Python, PyTest and unit test do this, and in old JUnit 3, test needed to be prefixed TEST. That's not the case here. We have an annotation that tells us, hey, it's a test. So let's follow the principle of avoiding duplication. Don't repeat yourself, the dry principle. Get rid of the word test. We already have @test in front of everything. Now, this looks intuitive. For many people, there's a simple alignment. If you see here, we've got one test for every single method. But this is a very brittle and not very helpful testing approach. To understand why, let us imagine that instead of having the default constructor here, that I no longer need the default constructor. In other words, all of my field initializers do the right job. I don't need an extra constructor to do further construction work. All of the field initializers set the stack up in a well-defined state. At this point, I don't need to write the constructor. Now, what happens to this? Does this mean that I'm now testing because the compiler allows us to have that? Am I now testing the compiler? That seems a little odd. I'm testing a thing that is not there and is not explicit. We might be tempted to do this. Except, think about it for a moment. The functionality hasn't changed. We've distracted ourselves. We're not focusing on how we use the class. We're focusing on how it's presented in terms of syntax. And it can be presented with the same behavior using two different syntax forms. So we should focus on the class's capability. Okay, so maybe people say, what about can be constructed, can be pushed, can be popped, has depth, has a top? Well, that's also not true because, again, this is a little bit vague, but also it can't always be popped. An empty stack in our definition can't be popped. So it can only sometimes be popped. And it doesn't always have a top. It only sometimes has a top. So if you look at these names, these are terrible names. They don't really tell us what's going on, but they're hiding behind lots of words. We need to think about this from a requirements point of view. So let's talk about requirements as a kind of structure. Given when then is a very common refrain. It's something we get from behavior-driven development and Dan Terhorst North. But it's also a reflection of the use case style of the 1990s, precondition, trigger, postcondition. It's a way of describing what we're expecting. It's a story. It's a three-part story. Given an empty stack, when an item is pushed, then it should not be empty. Should is a little bit of a weak word. Sometimes people quite like it. It kind of suggests maybe it's okay not to have it. Sometimes people strengthen it with a must. I prefer a simple, more logical style, just a statement, a proposition of what must be true. Then it is not empty. Now, we have a bit of a problem here because then it is not empty. Yeah, that's true. But it's a relatively weak test. And what I mean by weak test, let me show you what a stronger test looks like. It has a depth of 1. Okay, now notice there is a very subtle difference here, but there's a difference in strength. It is not empty basically says the depth is greater than 0. If we're dealing with a 32-bit int, there are 2 billion values that are greater than 0. Only one of them is right. 2 billion of them are wrong. So notice this is what I mean. It's a weak test. It's true that it is not empty, but that's not the whole truth. So we have what would be termed, what we could term an underfitting test. It lets too many error cases through. It doesn't really describe what's going on. Our job here is to be more precise. But even it has a depth of 1 is not particularly precise because we haven't said anything about, well, we pushed something onto it. Is that it? Well, no. The top item is the item that was pushed. Ah, right. So this is a conservation rule. I took an empty stack. I put something in it. The stack is no longer empty. It has one item, and the item that is in there at the top is exactly the one that I put in. It has not been transformed in any way. Right. This is a precise test. Now, we might take the words that you see on the screen and throw them together, which is not going to be very helpful for anybody as a name. Underscores make this more readable, regardless of what convention you're using, whether you're using camel case or not. But often we can find a way to shorten it. An empty stack acquires depth by retaining a pushed item as its top. Sometimes we need to come back to the test again and again to improve its name. As I said before, you're learning how to talk about the abstraction that you're building. Don't expect to have the best names and the perfect tests first time. Expect to come back to them and refine them. So what's that going to look like? It's going to look something like this. We take a new stack, we push a string on it, a rock, in this case, given I've used rocks. The depth is 1 and the top element is rock. And if we look at all of the test cases, we end up with a new stack is empty, an empty stack throws when queried for its top item, an empty stack throws when popped, and so on. Now, there's a nice feature in JUnit 5 which actually allows you to annotate the class so that if you use underscores, you'll notice the display name generation there is replace underscores. It actually will, in the output, replace the underscores with spaces. So it will convert this to a conventional sentence. And so therefore, in our output, we get, when we pass and we're on verbose or when we fail, we will get a new stack is empty, or the last one, a non-empty stack on popping reveals tops in reverse order of pushing. That's a very precise specification there. We can go a step further. We can recognize that with this, we're actually talking about effectively a state model. So in this, in this, we've actually got a story, a 3-part story, and I want to talk about that story. So 97 Things Every Programmer Should Know. It's just over 10 years ago I edited this book. There's this really nice piece from Jared Mazaros, Write Tests for People. And he describes each test, for each usage scenario of the test. 1, describe the context, the starting point, or the preconditions that must be satisfied. 2, illustrate how the software is invoked. Show me the code. It should be example code. 3, describe the expected results or post conditions to be verified. In other words, show me the outcome. And we could write it like this. If we wanted to put comments in to break it up, I don't necessarily suggest people use comments. Normally a blank line is enough, but sometimes the comments are quite a good ritual to help you think about the structuring of your test, especially when you're acquiring this as a habit. So this is sometimes known as the 3 A's, arrange, act, assert. But it's already actually identical to given, when, then. We've already seen this before. It's the same structure. We're effectively, when we're writing unit tests, we are writing a specification for our class. We are writing a set of requirements, not at the system level, but at the object level. We can go a step further, though. We're thinking specification. There's a rather nice piece in 97 Things by Nicholas Nielsen, Thinking in States. He observes that in most real-world situations, people's relaxed attitude to state is not an issue. Unfortunately, however, many programmers are quite vague about state too, and that's a problem. We often overlook the idea that there is a state model in our code, and we don't model it. I'm not saying that you need formal models, but I am saying that we are often not aware. We try and solve the code's problems at the code level rather than taking a step back and going, well, what's the state model here? What's the life cycle? The life cycle of a stack is actually not very exciting. It's new. You create it, it's new, it's empty, and then it's non-empty. And there are various operations. When you push on an empty stack, it becomes non-empty. On non-empty, you can perform all the operations, depth, top, push, and pop. When we pop and the depth is 1, we become empty again. And there is also, you'll notice that there is no operation listed for top and pop. From a design point of view, from a specification point of view, these are not specified, but actually from our design point of view, we're going to say, you know what? These are error cases. They are well-defined error cases. If you are working in a language where undefined behavior is normal, like C or C++, you might choose to do something differently. But honestly, as much defined behavior as we can have for the error cases is normally more helpful than less helpful. But more importantly, what can we do with this? Well, we can structure our tests hierarchically. In testing frameworks, JUnit and JUnit 5 is better at this than JUnit 4. I really can't remember about JUnit 3. I wasn't using this technique with JUnit 3, but I was using it with JUnit 4. We can do this with NUnit and C#, nesting. And JUnit 5 makes it very easy to express this. And there are a number of different frameworks that allow you in different languages to at least have 2 levels. I've mentioned the Google test 2-level naming. If I'm using PyTest in Python, I will typically take advantage of having test methods within classes and use the class as the top level and then the nested methods within that. And you'll see that here we have reflected the state model perfectly. And this is how we get away from having the problem that we often have of having far too many test cases, just lots of flat test cases, hundreds and hundreds of test cases, all at the same level with long names that are very repetitive and duplicate many parts. Here we've got something slightly different. We factor out a new stack. We factor out all the ones that are to do with an empty stack. We factor out all the ones that are to do with a non-empty stack. So we create this nice hierarchy that reflects the state model. A new stack is empty. An empty stack throws when query for its top item. An empty stack throws when popped. Okay, a non-empty stack on popping reveals tops in reverse order of pushing. It's a much more expressive model. It's much more powerful. So this teaches us that given can be used to group tests for operations with respect to initial common state. We can also use that to factor out common setup code. Okay, we have a lot of common setup code, particularly useful for complex tests where we are dealing with large authentic data sets and that needs a lot of setup. Or if we're doing this with integration tests, which require external setup, connection and things like that, having that common initial state can be very helpful. Factor that out. Use that as the driver. Don't just use given, when, then to order the inside of a test case. You can use it at the top level. So we factored out by given, but you can also make it factored out by when. What does when do? Well, when is factoring out by common action. Instead of, for example, with the stack, I could have said, well, I'm going to group together pushing on a stack. I'm going to group all the pushing operations together and then popping from a stack. I'm going to group all the popping ones together. Put another way, when pushing, and then everything to do with that on empty and non-empty. When popping, from empty, from non-empty. So I could use the when as my top level, my root level, if you like, for my test. So test nesting is very powerful. And of course, if I've used given and when, I can also use then. Well, actually, we've kind of already seen this. Then is the outcome. A year is a leap year if, okay, then it, if you like, then it is a leap year. I've finished with the conclusion. I would say that in tests, normally grouping by given and when are the most common, but sometimes then group together according to the outcome. That's what the reader wants to see. And again, that takes us back, structure and interpretation. We have created a structure where the interpretation is leading the reader's eye to understand what is important. Okay, the outcome is how we group it. Or in this domain, the state model is the most important. Now, let me give you another very simple example. I won't go into in detail. I want to talk, instead of a stack, I'm going to talk about a queue. What is the language of a queue? A queue, we can create it. It has a length. Okay, a queue is horizontal, whereas a stack is vertical. It has a length. We're also going to say it has a capacity. We're not going to have an unbounded queue. Okay, imagine we're doing this for inter-thread communication. You don't want to have an unbounded queue. That just means that if there's something wrong, you will end up filling up all of memory with a queue. So give it a finite capacity. Length, a capacity, and then we can enqueue or dequeue. Okay, so we can push on or pop from. So we've got a very simple model here that we can kind of consider. And that will look kind of like this. If I do this in C#, we must always initialize with a capacity. That capacity must be non-zero. It must be positive. We have a length. We have a capacity, which is the maximum. The length, when the length is at the capacity, it is full. We can enqueue and we can dequeue. And enqueue can fail with false if we are full. We can enqueue no more. And dequeue, it's not an error case. It's, yeah, I'm sorry, you tried to dequeue, but there's nothing here for you to receive. And you might think, okay, I've seen this before, Kevlin. I know what you're going to do. You're going to show me this diagram and you're just going to change a few of the words. It's just like the stack. No, it's not. Or rather, yeah, at a distance it is. But as we zoom in, we'll see there are some differences. First of all, we have the difference that there is a guard on construction. It means construction can fail. There is a criteria for it to fail. Okay. But the second thing is non-empty is where all the fun is at. That's where all the activity is at. It turns out that we have two different kinds of non-empty because we have an upper boundary. In other words, we have a nested state model. Non-empty, you can be full or non-full. The behavior of a queue is different when it is full. It accepts no more enqueuings. When it is non-full, it accepts enqueuings. So we have a hierarchical state model. It is nested. And I can express this in NUnit using this structure. Let's just get rid of the all the structure here. A new queue is empty. A new queue preserves positive bounding capacity. A new queue rejects a zero bounding capacity. A new queue rejects a negative bounding capacity. So we've got all of these ideas that are visible there. An empty queue looks very much as we would expect. But the interesting one is the nested one. The nesting also applies within the tests. A non-empty queue that is not full becomes longer when value enqueued, becomes full when enqueued up to capacity. A non-empty queue that is full ignores further enqueued values, becomes non-full when dequeued. And a non-empty queue dequeues values in order enqueued. In other words, what we have here is a nesting structure that reflects an interpretation of the model. We can understand it. So let's close with one other example. And you might think, okay, where's he going to go next? I want to go back to a single function. And I want to address one of the most overused examples when it comes to coding katas, Fizzbuzz. If you're not familiar with Fizzbuzz, this is a lovely quote from Richard Dalton. Fizzbuzz was invented to avoid the awkwardness of realizing nobody in the room can binary search an array. It's a very common interview question. It's a coding kata. Essentially, it is the idea. It's originally a drinking game, but slightly harder than coffee. And it's a counting game. 1, 2, 3, 4, 5. Well, that's how you normally count. But what we do is everything divisible by 3, we replace by buzz, or fizz, sorry. Everything divisible by 5, we replace by buzz. Everything divisible by 3 and 5, we replace by Fizzbuzz. Okay, that's it. And everything else is returned as a string. So if I do this in Python, what you see on the screen is a nice simple implementation. It's not the hardest programming problem in the world. But people also use this as a bit of fun for exploring alternative approaches. This is one of my favorite ones that just uses the table lookup. There are there's no conditional branches in here, and it just uses a simple kind of table lookup plus a Lambda application. These have the same functionality for the domain that is of interest. So how do people go about writing this? Well, most of the time when people write this, and I see people doing this, I've seen live demos, I've seen YouTube demos, they'll start off with the first test. Test that result for 1 is 1. Okay, assert that Fizzbuzz of 1 is 1. So just for context, I am using PyTest here. I don't really like using unit test. By the way, if you have a choice between using the unit test that comes with Python and using PyTest, then always choose PyTest. It's much, much better. Unit test is kind of like a Java version, or it's a Python version of a Java framework from about 20 years ago. Okay, it's based on JUnit 3, and honestly, Python is a much better language for writing a testing framework than pretending to write Java in Python. It turns out Java is the best Java, and Python is just great at being Python. Trying to fake Java in Python gives you stuff like unit test, very non-idiomatic, very non-Pythonic. So I can just write straight functions. Here I have to use the prefix test because that is the way that PyTest picks up its tests. The name test must occur at the beginning. To get the propositional style, I normally encourage people to think in terms of test that. Test that something is the case. Test that when you do something, there must be an outcome. So test that result for 1 is 1. And I find that the test that is quite a good thinking habit or word habit to get into in these cases. Okay, so test that for 1 is 1, result for 1 is 1, test that result for 2 is 2. Okay, this is not a very interesting set of test cases. Test that result for 3 is fizz. Okay, so finally we see fizz. Test that result for 4 is for, 5 is buzz, and so on. And then we build up a set of test cases. This is actually, I mean, this is absolutely fine to write while you're learning about it, but this is actually a really bad set of test cases. It makes things that are not significant that makes them significant. So 1 is not significant, 2 is not significant, 4 is not significant. The only numbers in the domain of Fizzbuzz that are significant are 3 and 5, and 3 times 5, 15. That's it. 1 is not important, 2 is not important. These are just not divisible by 3 and 5. But what we've done is we've ended up with these very pedestrian, very dull tests, very repetitive, very hard to maintain. These tests do not teach us what the domain is. So perhaps we write our code like this, our test code like this. That's fine. But take a step back. What we're trying to do is communicate an understanding of the domain. What is the shape of the domain? What are the constraints? What are the properties? In this case, we're going to use a more property-based style of thinking. We're going to do this in terms of logical predicates. Let's write this one out in English. For Fizzbuzz, every result is Fizzbuzz, Fizzbuzz, or a decimal. Is that true? Yes, it is. That's it. It's a decimal number. It's Fizzbuzz, buzz. That's it. That's the only set of possible results. Okay. Every decimal result corresponds to its input. So if I've got 11 as a string, then the number that it was input must be 11. So therefore, we cannot end up with 13 transformed to 11. So there's a direct correspondence. It's a simple transformation. Excellent. Every third result contains fizz. Every fifth result contains buzz. Every 15th result is Fizzbuzz. Right, we have just constrained a lot of the domain, but not enough. We need 3 more test cases, or rather 3 more constraints to fully characterize it. The input for every fizz is divisible by 3. Okay, there are no fizzes that occur that are not divisible by 3. There are no buzzes that occur that are not divisible by 5. And every fizz buzz that is present must also be divisible by 15. Notice that these 3 are not automatically a consequence of these 3. In other words, Fizzbuzz is constrained by these 8 constraints, or these 8 properties. I'm also going to, so here I've got another feature which you'll find in many modern frameworks, JUnit, NUnit, PyTest, and so on, where I can parameterize the test. Normally when people give Fizzbuzz as a problem, they give it over the range 1 to 100. Okay, so we're going to do that range 1 up to, but not including 101. So we're going to parameterize, we're going to pass in a value. So this will automatically execute 100 times with the values 1, 2, 3, 4, all the way up to 100. We take the result, Fizzbuzz, and we assert the result can be found in this set, Fizzbuzz, Fizzbuzz, Fizz or Buzz, or Fizzbuzz, sorry, or the result is decimal. Okay, that's a direct transcription of the name on the previous slide. Every decimal result corresponds to its input. We take the result, Fizzbuzz. If it's decimal, then we assert that the integer conversion is equal to the input n. Now, it turns out there's another way of writing this. I can continue in this style, or I can write it like this. What I can do is I can use Python comprehensions. If you're not familiar with Python comprehensions, don't worry about it. Just understand that what I've done here is I basically said, I'm going to pass in every integer and the Fizzbuzz of every integer into n and result, and I'm going to just assert that that is part of this set. It's either in the set Fizz or Buzz or Fizzbuzz, or it's decimal. This one is a little more interesting. I'm going to pass in n and the Fizzbuzz, or I, and the Fizzbuzz of I, for all those numbers, only if that result was decimal. So I'm only going to pass the decimal. I'm going to ignore the Fizz, the Buzz, and the Fizzbuzz. Then we have every third result contains Fizz. Well, I can step through my range, 3 up to 101 in steps of 3. Every third one, every single one that comes in here must contain Fizz. Same deal for 5s, okay? 5, this counts 5, 10, 15. All of those should have a buzz, okay? And then every 15, 30, 45 should be Fizzbuzz. And then the reverse check, okay? All of those that are equal to Fizz should be divisible by 3, okay? The same for those buzz, divisible by 5, and every Fizzbuzz should be divisible by 15. And that gives us a set of 8 test cases that correspond directly to what we described as being the defining characteristics or properties. This style of testing is actually a little similar to property-based testing. It's actually similar to the leap year example. It is this idea of focusing on a specification. And historically, while we may, people often talked about, we focus on computer science as being algorithms and data structures, very centric. And Nicholas Wirth, the inventor of Pascal and Modular 2, in the 1970s, he wrote a book called Algorithms Plus Data Structures Equals Programs. But we're at a point now, really, where we need to focus on this idea of structure plus interpretation is equals programs. The world is a lot richer and a lot deeper. And what I hope you got from this talk is the idea that the structure and the interpretation does not just come from within the program. It comes from the tests that we surround our program with, that they can actually bring to life how the code is used, how it is intended to use. And indeed, many of the things that would normally pass as comments or check-in comments can actually become living. They can have a life of their own in the names and structure of our test cases, which is far more powerful. People tend to pay attention to things that fail and pass in the way that they don't to just ordinary comments. So thank you very much for that. Okay, I think we're good. I think we can take some questions. Andre, if there are any questions, otherwise that was really short and good fun.
Yes, I hope you hear me.
Yes, I can hear you.
Mm-hmm. Okay, cool. Yeah, we have quite a few of questions, and I will read loud. And first of all, Ann Ray asks, hello, Kevlin. The subject of your report is test cases. Do you find test case documenting important? I mean, test plan. If yes, would you please tell what is the definition of good test case? Prepare the test data, well described given when then script, attached file samples. What else can make it excellent?
Okay, so I'm gonna go with the idea that for me, the best form of documentation of a test case is a test case that executes. So in other words, it's the idea, very much as the subject of the talk, is try and put anything, write your test plan down in an executable form. In other words, code it. That is, if we can get closer to code, that is the most important thing. I certainly, I worked at a company many, many years ago, not as a tester, but I remember somebody teaching how to write test plans. And it seemed like a very human and labor-intensive process for something that computers are very good at. So my general feeling is automate. If you are still writing out test cases, then what is it we can do to automate? Whether we are using tools like Cucumber, or whether we are working with developers to create test cases that are in our target language but can be read. So in other words, the best test case is the one that executes. For me, that is where I would always start. When it comes to choosing test data, I gave you the tulip category, the 4 categories. There's clearly more work to be done on how you break down those. There's a couple of things I didn't mention. For example, choose data that is representative of your domain. What I mean by that is ordinary values. So if somebody says, year, okay, well, 2021, that looks like a year. 5 does not look like a year. Now, 5, indeed, in our problem model is a year. It is a year, and it's potentially something we could include. But when we want the reader to think, okay, domain, I need to be thinking in this domain, 5 is not going to help them. But 2021, yes, I understand that as a year. In fact, there's a simple test that you can always do is whenever you see a number that is also the year of your birth, okay, it is very difficult to not see it as a year. Okay, so today, for example, it's my older son's 90th birthday. So he was born in 2002. If he sees 2002, he does not see it, that's the number 2002. He sees it as the year of his birth. Okay, mm-hmm. There are certain numbers you can't help. You don't think, that's an int. You think that's the year of my birth. The point there is that's an example of placing a person inside the domain. If we have code where we are dealing with people's names, for example, don't use foo and bar. Nobody's called foo and, I hope nobody's called foo and bar. That's terrible names to give to your children. Or A and B. Use data that looks like names. Use years that look like years, names that look like names. In other words, the idea is once somebody who is reading your tests sees that, they are immediately in there and they immediately start thinking along the right lines, but they will also catch you out. They will say, wait a minute, if that's names are a really important one, people often get these wrong. And say, wait a minute, my name, for example, does not fit inside a passport. Or my full name does not fit inside. It's too long. So you can bet that would be one of the first pieces of test data I put in just to see, does this fail in this case? Because I'm making it real. If you just give me A and B, I go, okay, A and B. I just go along with it. But make the person think in that domain, because if they know something that you can take advantage of, you want them thinking along those lines. So just to summarize, for me, the best test plans are the ones that are code. Because that's the best way to capture the plan. Sometimes we need to move away from just pure code, and that's where a lot of tools like Cucumber kind of fit in. They can help us. They can increase the conversation across the team. But that is the best place because people pay attention to them, whereas traditional test plans, people ignore. That is unfortunate. No matter how much good work goes into them, they get ignored. So, yeah.
Okay, thank you. I was thinking that writing a good test case that is giving a context is similar to preparing a good presentation. That is giving a context and understanding. What
I think that's a really good way of looking at it. And also, like a presentation, the more you start looking into it, the more you understand about it. And that again is this idea: do not assume that the first time you come to something is going to be the best time. As you say, the key to a good one. Good is where we're always heading, if you like. The first version may not be good, but it's better than not having something. Once you have something, you can start improving it.
Okay, next question is Andrei asks, how are you handle with flaky tests? How do you handle flaky tests?
Flaky tests that are not predicted. Right. So typically, the first thing you need to do is understand why is my test flaky? Why do we have tests that are what we might call intermittent? Sometimes they pass, sometimes they don't. Okay, that's the worst kind of test. You want, I put it this way: I want my greens to be green and my reds to be red. I don't want them to kind of like change between the two. The first thing is, why is that? That is normally an indication. There's normally a couple of sources that will lead to that. One of them is that we are dealing with a test that is not a unit test. In other words, there is behavior that is not under our control. What kind of behavior is not under control? Well, the network's not under our control. If we have multi-threaded code, then guess what? Multi-threaded code is not under your control. Strictly speaking, you can't unit test multi-threaded code. You can integration test it, but you do not control the scheduler of the operating system. So therefore, you cannot guarantee and recreate the exact situation that led to a failure. So intermittent failures along those lines. So the first thing there is to separate out, is this a unit test? In other words, is the reason for my intermittent failure, is the reason for flakiness the fact that it has external dependencies? And once we've established that, the next question is, and should it have these dependencies? Because what we may find is the logic of our code should not depend on external dependencies. We may be saying, oh, well, we're getting an XML file, and the file may or may not be there, or the file may not have read permission. Or it's like, wait a minute, XML is not a file format. XML is a text format. So does our code deal with files, or does it deal with the text of the XML? Because many people assume, our configuration, for example, comes from a file, or our configuration comes across the network, and it's in XML. It's like, yeah, but there's two things there. There's not one idea, there's two ideas. One is, how do we parse the XML? And that should never be flaky. It should be well determined. For a given XML string, there is only one outcome that is defined. So let's separate it out. And so now we discover, here's the unit testable bit, here's the non-unit testable bit, the integration bit. And that's fine to separate it out. It's a separation of responsibilities, a separation of concerns. So what we do is, by examining the flakiness of our test, we realize, most of the logic is not to do with the bit that is flaky. Let's separate those two out. It improves our design. The other main reason, by the way, you might end up with flaky tests is that you rely on random numbers. I'm not going to say relying on random numbers is wrong. Sometimes we use it for test generation of large data sets. But always make sure that you have a test that every random number you use, you are in control of the seed and you can recreate the seed. You don't actually want it to be random. You don't want it to be unrecreatable. You should be in control so that you can rerun it and re-authenticate that that particular sequence causes a problem. So just take control. So if you're using random data generation, using random numbers, make sure you're in charge of the random numbers, okay? Make sure you control and have full information about the sequence so you can recreate it.
Okay, I guess it should be the last question. We have quite a few more questions, but let's discuss it in Zoom.
Let's discuss this in the Zoom channel afterwards. So let's take the last question now.
So until we aren't interrupted by organizers.
Oh yeah, until the organizers pull the plug, let's keep going.
Yeah.
So hi again. Hi. So, Kevlin, thanks for this nice talk. It was really, really productive, I think. Yeah, so there are more questions in chat, and I think you can continue in discussion zone in Zoom, so you can move there. Thanks to you.
Okay, brilliant. Thank you very much. I'll see everybody in Zoom.
Bye-bye.
Thanks.